Continuing on with day 2 for chapter 16, we'll be applying random variables to the normal model. Another concept way back from unit 1 is that when we had our data set and we added or subtracted a constant to every number, the mean changed, but the variance and the standard deviation stayed the same. Okay, a lot of things changed when we added or subtracted a constant. The mean changed, the quartiles changed, basically measures of center changed, measures of location changed, like mean, median, minimums, maximums, those all changed. Measures of spread such as IQR, standard deviation, things like that, range, those didn't change. Okay, when we multiplied a value, everything changed. Now, when we talk about variance, okay, since variance is the square of the standard deviation, when we multiply a constant, okay, the standard deviation increases by that constant, and the variance increases by the square of that constant. So let's apply this to random variables. Now, first off, we're talking about independent random variables. This is the word that keeps coming up. We pretty much always need things to be independent in statistics. So when we combine two or more independent random variables, when we want to find the mean, such as adding two or more or subtracting two or more independent random variables, the mean is found logically. We're just going to either add or subtract the means of all these variables. Standard deviation or variances is not quite as logical. They're always going to grow. So if we subtract two random variables, we still add the variances. Okay, think about it as we're adding uncertainty. When we're talking about like the spread of variables, even when we're subtracting them, we're really increasing the amount of uncertainty in like how much there is, whether we're adding them together or subtracting them. Okay, and we always add or subtract, we always add the variances in order to find the standard deviation. Standard deviation is just the square root of the variances. All right, so how long do we expect to wait for our turn to get tickets if there's two customers in line in front of us and there's a mean wait time of 100 seconds with a standard deviation of 50 seconds? So the mean is logical to find. We're just going to take each customer's wait time and we're going to add them together. So 100 plus 100, we have a mean expected wait time of 200 seconds. Standard deviation is not quite as logical. So to find the standard deviations of independent random variables, we want to add the variances together. So we have one customer who has a standard deviation of 50 seconds, and then we have another customer who has a standard deviation of 50 seconds. So to find the standard deviation of our wait time, we add the variances for both of these customers. So the first variance is that 50-second standard deviation squared, and then same thing for that second customer. So we have both their standard deviation squared gives us their variances. We're adding their variances together, and then we're going to square root those two to the sums of those variances. That's going to give us a standard deviation of 70.71. So our expected wait time is 200 seconds with a standard deviation of 70.71 seconds. Part C, what assumption did we make about the two customers in finding the standard deviation? We're assuming that these wait times are independent. So for every dollar bet, this slot machine pays out an average of 92 cents, which means that the casino's profit is 8 cents per dollar played on average. The standard deviation for every dollar bet is $120. So to find the mean amount, if we play 5 times for the casino's profit, it would be just 5 times the mean of a single play. And a single play is just 1 minus that 92 cents that it's expected to pay out. They're making 8 cents per play. 5 times that 8 cents would be 40 cents. We'd expect the casino to win over the 5 plays. For the standard deviation, we have to add the variances of all 5 spins. The variance for one spin is that $120 standard deviation squared. That's a squared there. And then we have 5 spins. So it's 120 squared plus 120 squared plus 120 squared plus 120 squared. Okay, really we can just write this as 5 times 120 squared. squared. Okay, make sure you square the 120 first, then multiply it by 5. To find the standard deviation, the symbol here is sigma, by the way, we square root the variance. So the variance is what's on the inside here, 5 times 120 squared, square root it to get that standard deviation. So when we do this, 5 times 120 squared is going to give us 72,000. That's the variance. Square root of that gives us a standard deviation of $268.33. So if we were to play this machine 1,000 times a day, how much would the casino expect to make? They would expect a mean of 1,000 times that 8 cents per spin, which would mean they would expect to make $80. The standard deviation for their profit would be the sum of all those variances, which would be 120 squared plus 120 squared, etc., 1,000 times, which is really just 1,000 times 120 squared. We square root it, square root the variance to get the standard deviation, which gives us $3,794.73. All right, do we think that the casino is likely to be profitable? We're going to eventually talk about how to figure this out using a more mathematical justification. But when we look at this, we see that their profit of $80 is very small compared to the standard deviation. There's a huge amount of spread here, meaning that really it could go either way. And if we actually did the statistical mathematical justification here, we'd see that they have a slightly more than 50% chance on this machine of being profitable. So over the long run, they'd be profitable, but in a single day, it's slightly better than a coin flip of them coming out on top. Everything we've been dealing with so far have been with discrete random variables where they have set values that the variable can take on. When we have a continuous random variable that can take on any value within a specific range, we can deal with them for the most part the same. We're just going to apply a normal model. So here we're looking at a company that's packing and boxing stereos. So the packing process is modeled normally with a mean of 9 minutes and a standard deviation of 1.5 minutes. The boxing process has a mean of 6 minutes and a standard deviation of 1 minute. First, we want to find the probability that packing 2 consecutive systems takes over 20 minutes. And then next, find the percentage of stereo systems that take longer to pack than to box. So it had mentioned that the packing times were approximately normal with a mean of 9 minutes and a standard deviation of 1.5 minutes. Now we want to find the probability that if we look at 2 systems being packed consecutively, that it takes over 20 minutes to pack both of them. So first off, we want to find the mean, and the mean is just going to be the sum of both those means, which is 9 plus 9. Okay, so packing 2 systems will take a mean of 18 minutes. The standard deviation we'll find by adding the variances. So we're going to add 1.5 squared, that 1.5 minutes, square to find the variance. That's for the first box. Add for the second stereo, 1.5 squared, and that's going to give us a variance, or I'm sorry, a standard deviation for both systems of 2.12 minutes. All right, so now we have a new normal model. Okay, so we have a normal model for the probability of packing 2 systems consecutively, and it's going to have a mean of 18 minutes, and it has a standard deviation of 2.12 minutes. And we want to find the probability of these 2 systems taking over 20 minutes to pack. Okay, so this goes back to Chapter 6 in Unit 1. We want to find the z-score and use normal CDF to find that probability. Remember, with z-scores, we always subtract the mean. So we have 20 minus 18 divided by that 2.12. That gives us a z-score of 0.9434. And now we would go to normal CDF. That's under distribution in your calculator. So z-score, lower z-score of 0.9434, upper z-score of anything larger than 3. I usually put in 99. And that's going to give us the area that's shaded there. And I have 0.1727. Okay, so there's about a 17.27% chance that 2 consecutive systems take over 20 minutes to pack. Next, what percentage of the stereo systems take longer to pack than the box? So packing takes on average 9 minutes, boxing takes on average 6 minutes. All right, so let's start off by defining what our random variable is going to be. So let's call it expected value of the difference, D for difference there, and we're going to say pack minus box. Okay, so on average, we should have a difference of 3 minutes. The standard deviation for the difference between these two times, again, is the sum of the variances. Now, it doesn't matter that we are subtracting up here, we still add the variances. So the variance for packing, or the standard deviation for packing, was 1.5 minutes. That gets squared to find the variance. And then we're going to add, because variances always compound. We're always adding some uncertainty. We're adding the variance for the boxes. So standard deviation for the boxing process was 1 minute, square it to find the variance. That gives us a total standard deviation for both processes of 1.803 minutes. Okay, so now we use both of these to make our normal model. So we have a normal model that centers around 3 minutes with a standard deviation of 1.803. And we want to find out what's the probability or the percentage of stereo systems that take longer to pack than to box. And this part is a little bit of a logic question. Okay, if packing takes longer and boxing takes shorter, then when we subtract them, longer minus shorter, this should give us a positive number. So we're looking for a cutoff of 0, and we want to shade the positive side. So anything that's in the positive area means that packing has taken longer than boxing. So now, just like before in the last one, we find our z-score, 0 minus 3, divide by that standard deviation of 1.803, and we get our z-score. We'll get negative 1.667. Okay, go to normal CDF. That's going to give you the area of this shaded section right here, which is 0.9522. So there's about a 95.22% chance that the stereo systems will take longer to pack than to box.